whenever you want.
Yes, we're pleased to have Guillem speaking about Hopf algebras and equivariant Lagrangian Floer homology.
Yeah, thanks for having me here. I'm very happy to speak in this seminar. Yeah, so all I want to talk about today is joint work with Paul Kirk, Artem Kotelski, Mike Miller, and Wei-Kit Young, and it's very much work in progress. Okay, so let's start with equivariant Lagrangian Floer homology. Suppose you have a symplectic manifold with a pair of Lagrangians in it, L0, L1, and some extra assumption that makes it make Floer homology well defined. So different kind of assumptions you can make. Then in good circumstances, you have a Floer homology group associated to these two Lagrangians. Okay. Now the question, so in general, you have to make these assumptions, and the definition is more or less easy depending on those assumptions. But then you could ask the question: what happens if the symplectic manifold and/or the Lagrangians that you have happen to be singular? Okay, and then that's more difficult. So, for example, you could have something singular if your manifold and Lagrangians arise from a symplectic quotient. So let's say you have a smooth symplectic manifold M tilde that has a Hamiltonian action, and you take the symplectic quotient. Okay, and you have a pair of Lagrangian in it. You get a new pair of Lagrangians in the quotient, and maybe that will be singular. Okay, so for example, this happens if you do the Atiyah-Floer conjecture. You have the Atiyah-Bott moduli space of a closed Riemann surface, and it's singular, and that's why this conjecture is difficult. So an idea is that in these circumstances, you don't want to take actual Floer homology of M, but instead you want to replace it by an equivariant construction on M tilde. Okay, that's what you would call equivariant Lagrangian Floer homology. Okay, so there are several constructions of such groups that already appeared, and a lot of work by different people. So for example, there is one approach that uses the symplectic vortex equation. Okay, so it's work by Chilibak, Gayon Salamon, and Mundati Rieira, and then work from Fronfelder and too. There's another approach that uses infinity categories. That's due to Hendricks, Lipschitz, and Sharkar. Also an ongoing project of Fukaya and Daimi, who tried to prove the Atiyah-Floer conjecture. And then they're using some Morse-Bott theory and an adaptation of a construction by Austin and Bram. And then finally, you can also do some Borel construction if you take an approximation of EG, and then you can look at the cotangent bundle of this finite dimensional approximation, and you can use these to produce a construction. So construction like that appeared in symplectic topology by Viterbo, in work of Viterbo and Bourgeois and Ancha. More recently, Kim, Lau, and Chang define also a version of such an equivariant Lagrangian Floer homology, and also have another very similar construction, but it's work in progress. But today, I'd like to tell you yet another approach for defining such groups that's that's algebraic in nature. Maybe it's closer to this infinity category approach by Hendricks, Lipschitz, and Sharkar, but at least it uses algebra that's, at least to me, less complicated than infinity categories. So just use A infinity algebra. And I'll tell you why we're interested in this approach, and we'll see that it should be well fitted for defining a coordinate instanton theory. I'll tell you later. Okay, that's what we want to do. So here is another approach. Now this approach is inspired by a Morph theoretic construction, and the starting point of our construction is the following observation. So let's consider a compact Lie group G that acts on a smooth compact manifold X. So in this setting, the equivariant homology of X is defined as the homology of the homotopy quotient. Okay, so before quotienting by G, you take product with EG. And then there's a theorem by Guggenheim and May that tells you that this is actually the same as the homology of the tensor product of the chain complex of X and the chain complex of EG over the chain complex of G. Okay, and we would like to mimic this identity. So we'd like to write a formula like, take Lagrangian Floer homology as the homology of the Floer complex of L0, L1, tensor the complex of EG over complex of the group. Okay, that's the kind of formula that we would like to write in order to define this homology. But in order to do that, we need an action at the chain level. Okay, we would like the Floer complex to be a module over the chain complex of G. Okay, and that's we have a kind of a similar action, but with a Morse complex. Okay, so here is our main result. So, okay, we are going to work with Z2 coefficients, although we expect that it works more generally, okay, with Z coefficients. So the setting is we have a compactly grouped G, and we fix a Morse function on this group, small g, and then we have a symplectic manifold M omega that comes with a Hamiltonian action of G with a moment map mu. Okay, and then have a pair of Lagrangians in M. Okay, now we're going to make some assumptions on these guys. So first assumption will be that we want the identity element of the group to be a local minimum for the Morse function on the group. Okay. And then we also want to make some assumptions on the M and the pair of Lagrangians so that, well, mostly what we want is that the chain complex is well defined. So usually, I mean, there's two kinds of assumptions. We can assume that everything is exact, but then the manifold is non-compact, so we have to put some convexity assumptions on the manifold. And let's say, to make our life easy, the Lagrangians are compact. And we want the moment map to be proper, or another set of assumptions that you can make is monotonicity. So we want everything compact, everything to be positively monotone. And I'll tell you later what this Vanishing correspondence is. But also, so these are technical assumptions that makes Floer homology well defined essentially, and we'll see how it appears. Okay, and then we want to condition on the minimal Maslov numbers of these things. They should all be proportional to common integer that's bigger than 3. Okay, so under these assumptions, then have the Morse complex of the group, and it carries a structure of an infinity algebra for which the identity element, which is a critical point now, is a strict unit, in the sense that its differential is 0, it's a unit for the product, and when you plug in the higher infinity map, it goes 0. Okay, that's the first part, and then in this situation, the Floer complex of the two Lagrangians is an infinity module over this Morse complex with this given infinity algebra. Okay. So in this sequencing, that's great because now there's some work in Mike Miller's thesis that we can apply to produce equivariant Floer homology groups. Okay, so we're going to consider this infinity algebra, which we're going to call A, and we will have to divide by the unit. So denote by A bar the quotient of A by E, and then here are the right construction that we should do according to Mike's thesis. So in this setting, you can produce a bar construction if you have all this A-infinity algebra and two left and right A-infinity modules over it. You can produce a new chain complex. That's the bar construction, and I mean, roughly the differential in this thing is a sum of terms that looks like this. So basically, you just use all the new maps that you have, and that produces for you a differential. And we're going to use this where A is our algebra, M is the Floer complex, and N is a trivial module of the ground ring. Okay. Okay. Then there is a similar construction. That's co-bar construction. That's kind of a dual construction. And using these constructions, we can define three complexes that are the Borel complex, the co-Borel complex, and the Tate complex. It's kind of a mapping code between such things. And so, I mean, well, so I'll be very quick about, I mean, I'm not going to tell you more about this, but I invite you to read Mike's thesis appendix, which is well written. But the upshot is, in these circumstances, some algebraic construction will give you three homology groups for you. Okay, that's analogous to the different flavors of Floer homologies, for example. Okay. All right. Are there questions so far? No. Okay, so I'm going to continue. So, whoop, I think that someone wrote in my screen. Anyway, so yeah, so well, as I said, this construction of this infinity structure is inspired by Morph's theory. So maybe I'll first describe the Morph theory analog first. So here is the analog. Now suppose that you have a compact group acting on a smooth compact manifold, and you have a pair of Morph's function on each of these things, so f and g. So in this setting, we can show that the Morse complex of the group is an infinity algebra, and the Morse complex of X is an infinity module over this algebra. Okay, and these structures are such that when you take homology, when you pass homology, you recover the algebra and module structure induced by the multiplication maps. Okay, so you have a multiplication from the group times the group to itself that induces it's a group, the group operation, and the module, and then the group action mx. They induce push forwards in homology. Okay. So these are kind of chain level versions of this module and algebra structures. All right. So basically we want to find chain level versions of these. So what we're going to need is a chain level construction of the push forward in Morse homology. So so let's do that. Let's review that first. So and this is something that's not new. And for example, you can find something that's very close to what I'm going to tell you in Kronheimer and Morfka's book. So here is a setting. Now take two smooth manifolds M and N equipped with Morse functions, and then a smooth map from M to N. Okay, we'd like to define a corresponding map at the chain level, at the Morse chain level. Okay, so for example, M could be a circle and N could be a torus. Okay, and here in orange I have drawn the stable and unstable manifolds of the index 1 critical points, and maybe the map phi is mapping the circle to this green circle in the torus. So a priori, it's not related to the Morse function on n. But what you can do is you can take this image that corresponds to the unstable manifold of the index 1 critical point in the circle, and then you can let the flow of the gradient of G act on this, and we will observe something like this. Okay, so you see that almost everything in this green circle will fall to the minimum, except that the little arcs that hit the unstable manifolds that will concentrate along stable manifolds of the critical points. Okay, and so basically here, what you do, you would like to count these two blue circles here that will define the pull forward. Okay, so you can do that, and it turns out that counting these is equivalent to counting what would call Morse grafted lines. Okay, so this consists of couples of half lines gamma minus and gamma plus. So gamma minus happens in M, and gamma plus happens in N. These are flow lines, and they are related by the map phi. Okay, so this is how the construction works. So remember that we want to make sense of this algebra structure. We're just going to have to apply this construction to our multiplication maps now. So for the group first, you have this map, and though the group with Morse functions, just using the Morse function on G again. Okay, so here you can just take the function that sends xy to the sum of g of x and g and y. Okay, and then you want to do the former construction, and it turns out here that counting these grafted lines is equivalent to counting what I'll call multiplicative y. Okay, so the thing is that the component in G times G, it just has two components, gamma 1 and gamma 2. And you can kind of unfold these and then just give you these two things. It's just another way of writing the same thing. Okay. So that's for group. And then you have the action on G times X. And then here you would count something very similar, except that what's in red will happen in the group and what's in blue will happen in X. Okay. So the previous construction now gives you chain level products. Okay. And yeah, you could ask, are there actually algebra and module structures? So basically you ask whether these are associative, and or maybe asking strict associativity is too much to ask on the chain level. But the thing is that this will be associative, but only up to homotopy. Okay, and in fact, this will be part of an infinity structure. Okay, so how it works. So let's try to prove associativity first. So take 4 generators of Morse complexes, and let's try to look at associativity of, we do X, Y, and Z, and then the coefficient on T. So by definition, this is the same as counting this kind of broken Y's. That would look like this. Okay. And as usual, to prove that this is 0, you would like to recognize this as the boundary of a one-dimensional moduli space. Okay. So maybe this part is the boundary, is in the boundary of some moduli space, and then the second half is in the boundary of another moduli space. So basically, you just want to glue along these vertices V and W, I mean, along these critical points. So define A and B, the one-dimensional moduli spaces, to be the union over all possible lengths where you have glued things. So instead of having 2 semi-infinite lines, you would have a finite interval here. Okay, and same for B, you go on the other way. Okay. But the thing is, observe that when L equals 0, you have a simpler tree, and when L prime equals 0, you will have the same thing, and this is because the product is associative. Okay, so in fact, these two spaces, you can glue them along the part where the lengths are 0. Okay, I'll give you a moduli space called M of x, y, z, t, and you can compactify it. So if you compactify, you have a boundary, and that corresponds to the thing that we just saw. But in fact, you can have more breaking than that, because you can also have breaking at the semi-infinite trajectories. So you can also have things like that. Okay. So then that implies that these product structures are associative, well, up to homotopy, and the homotopy is given by a mu3. Okay, so that's the third infinity relation, and roughly this kind of things would give you the mu3. Okay, how it works. So now let me tell you how to define a Fluorite infinity structure. So first, well, so the first part of the infinity structure would just be the Morph differential. And then now if you take an integer k bigger than 2, you can, when you have the moduli space of all trees, so the trees with k plus 1 leaves, and these are metric rooted ribbon trees, and that means that whenever you have a finite edge, you also have a length associated to this edge. Okay, so this is well known to be a polytope. Okay, that's the sociahedron. I mean, at least when you compactify it. And then if you take a bunch of critical points, you can define a moduli space associated to these critical points. And I'll tell you later what exactly this moduli space, but it turns out that this moduli space will have a dimension. Okay, that's given by the following formula. And then with these moduli spaces, when there are dimension 0, we're going to use them to count. I mean, we're going to count them and use them to define the infinity structure. That's the way it works. Okay, so we're going to define the operation mu k that takes k inputs in the Morph homology and spits out one output by the count of these moduli spaces when they are dimension 0, and otherwise it's 0. Okay, any questions so far? No? Okay, so let me continue. So now let me tell you how this moduli space is defined. So this consists of pairs of a tree in this moduli space of trees, and the map gamma bar that goes from the tree to G, and I'm going to tell you what this means, and I'm going to tell you what the conditions are to satisfy. So for example, the tree gamma could look like this. Okay, could have this shape, and then there's two finite edges, and they'll have finite lengths L5 and L6. Then here a map gamma from the tree to G will consist of 7 tuple of maps where, I mean, this corresponds to gamma 1, gamma 2, gamma 3, gamma 4. This will be semi-infinite trajectories, Morph trajectories. And then these two things will be maps from the closed interval of length L5 and L6 to G. And then gamma 7 will be, again, another infinite Morph trajectory, but on the other direction. Okay, and then the condition that this should satisfy is that, well, so these are all flow lines for a pseudo gradient of the Morph function, and for transversality region, we would need these pseudo gradients to be domain dependent. Then at the limits, so at the here at the inputs and the outputs, you want the critical point that you start with to be at the limits, at the ends. And then you want these things to satisfy multiplicative relations at the vertices. What I mean here is, for example, at this vertex, you could look at gamma 1 of 0, gamma 2 of 0, and gamma 5 of 0, and you want that the product of gamma 1 and gamma 2 equals gamma 5. How it works. And same here. So here we correspond to gamma 5 of L5, that's the other external point. And then times gamma 6 of L6, you want it to be gamma 7 of 0. Okay. So these are how these moduli spaces are defined. Okay. And then it turns out that these mu maps, these mu k maps are actually an infinity maps, so in the sense that they satisfy the infinity relations. Okay, so here I've done the first relation is that mu1 is a differential, that's well known. And then the second infinity relation tells you that mu2 is actually a chain map. And then there are other relations. So we just saw the third relation that was telling us that mu2 is associative to homotopy, but in general, the infinity relations look like this. Okay, you sum over all the possible ways to break a diagram into two pieces, mu k1 and mu k2. So if you fix this length k, you have a relation like that. You sum over all possible ways of decomposing k plus 1 into k1 plus k2, and also over all the possible places here to stick in mu k2. Okay. All right, so that's the infinity structure on the group. All right, now let me tell you the infinity module structure on the Morph's homology of X, where X is a space acted on by G, and it's defined very analogously. You would really count the same kind of things, except that now what happens in the top right, in all the right part, this blue part here that I draw, now it happens in X instead of G. Okay. Otherwise, it's very, very similar, okay? And then in this part, you use the multiplication mx, okay? So then you get the module structure in the sense that it will satisfy a very similar relation as before, okay? It's just exactly the same, except that now what happens in the right is in blue. Okay. So that is how you can define this module structure on the Morse complexes. Now we want to transpose this construction to Floer homology. Okay, so in order to do that, we're just going to use the well-known dictionary between Morse homology and Floer homology. So this is how it works. So if you have a smooth manifold X and you want to do Morse homology in X, that's the same as doing Lagrangian Floer homology in the cotangent bundle. Okay, in the sense that if you have your Morse function, it will give you a Lagrangian in the cotangent bundle as a graph of the differential, but you also have the graph of the zero section, that's a second Lagrangian. Okay, and the critical points are in one-to-one correspondence with the Lagrangian intersection, and then the flow lines will become J-holomorphic disks. Okay. So that's well known, and but now, so the question is, what happens to these grafted lines that we saw before? It turns out that a grafted line will become a quilt. Okay, so these are kind of objects that were defined by Verheim and Woodward. So these are pairs of pseudohomomorphic maps happening in the cotangent bundle of M and the cotangent bundle of N, but they are seamed together by a Lagrangian correspondence. Okay, so if you take a point in the middle, you have two images in T star M and T star N, and then you want them to lie in the Lagrangian inside this product, that's the conormal bundle of the graph of phi. Okay. So this is how these things correspond in Floer homology. And then a particular case of grafted line are these multiplicative trees. Okay, so in the same vein, so what would correspond to a multiplicative tree as before in Floer homology would be what we'll call a pseudohomomorphic foam. It would look like this. It's like a quilt, except that now you have seams, but they can touch more than 2 patches. Okay. And here, I mean, you can just use this conormal abundance of these graphs of multiplication maps. Okay, that's a pseudohomomorphic foam. Okay, so it turns out that so that will give us a construction at least for cotangent bundle, but it turns out, and that's a good surprise, that so for this, we need this conormal bundle. It is not that you will have similar correspondence even if we're not in a cotangent bundle. So in general, well, it turns out that this, in the case of a cotangent bundle, this is the same as what's called a Vanishing correspondence. Okay, so Vanishing correspondence is a Lagrangian correspondence that you have anytime you have a Hamiltonian manifold, and it's a way to encode the action. Actually, it's like the graph of the action, but the component in T star G encodes the moment map. Okay, so the Hamiltonian action is entirely determined by this correspondence, and it consists of points. So QP is in the cotangent bundle of the group, and then a point M in M, and M prime also in M. So here the condition is M prime is Q times M, and then if you look at P, that's a covector, and if you shift it back by Q inverse, you get an element in the Lie algebra you want in the dual of the Lie algebra, and you would like it to be the moment map. Okay, so it turned out that this is a Lagrangian submanifold, and we'll be able to use it in our construction. Okay, so due to these correspondences, we can just transpose the previous construction in the Floer setting. Okay, so in fact, I'll just define mu-k maps by counting these kind of forms. Okay, with everything being decorated by what you need. So what's in blue will happen in your Hamiltonian manifold M. What's red will happen in the cotangent bundle, and then so there are different kind of boundaries. There are these green ones that you will use these vanishing correspondences. And then the other part, so here, well, you use in this side, you will use L0. Here you will use L1. And then on the other side, you will use the graph of your Morse function and the zero section. Okay? So that defines for you an infinity structure on chain complex. Okay. Another thing is, it's interesting to notice that in general, in Morse homology, there's another very similar infinity structure that you might have already seen. Usually it's in cohomology. It corresponds to the cup product. Okay, but since we're working on homology, for us it will be a coproduct. Okay, so basically, I mean, at least formally, it works the same as what I just described, except that instead of using these multiplication maps, you would use these diagonal maps. So just take any smooth manifold X, does not need to be a group. Just take the diagonal map, and then it induces a push forward in homology, and that's a coproduct. Okay, so that's a homology level, and then you can have a chain level version, and it's just very, very analogous to what I just described, except that it will be an infinity coalgebra structure, so arrows will go on the opposite side, and you basically count trees like that, except that here in a vertex, we used to use the multiplication maps, and here for the diagonal, the condition just becomes that the 3 values agree. Okay. So that's how it works. And yeah, let me just mention that this is in Morse homology, but then the analogous structure in Floer homology is what's known to be the Fukaya category. Okay, and because we're not doing cohomology but homology, for us it would be an infinity co-category, so to speak, in the sense that instead of having composition maps to compose morphisms, you would have decomposition maps, you would decompose morphisms. Okay, that's what reflects this coalgebra structure. Okay, so the interesting thing is that these two structures, they share the same differential. I mean, their differential is just the Morse differential. Okay, and then you could ask, well, how are these two structures related? Are they part of a larger structure or something like that? Okay. Yeah, and so that's where Hopf algebras enter the picture. So let me recall what a Hopf algebra is. I mean, I'm not going to give the full definition, but the prototype of a Hopf algebra comes from the following situation. So let's say you have a group, Lie group, compact Lie group acting on smooth compact manifold X as before, then look at the induced action at the homology level, and then homology of G is the prototype of a Hopf algebra, while the homology of X will be the prototype of a Hopf module. Okay? So a Hopf algebra would be a vector space, let's say, with a multiplication, a co-multiplication, a unit, a co-unit, and an antipode. Okay? So this is how this map goes. So for example, the product goes from H times H to H. Okay, I will denote it this way. The co-product will denote it this way, which will really be analogous to what we did before. And then you have unit for the product and co-unit for the co-product. And there's something else called the antipode. And that what would be the map induced by the map from G to G that takes G to its inverse. Okay, so Hopf algebra is such a data of maps, and they satisfy some properties. I mean, basically, you know, you want product to be associative, co-product to be co-associative, units to be units, etc. And in particular, there is one relation between the product and the co-product, and it can be seen in the following diagram. Okay, so if you first do the product and then do the co-product, it's actually the same as first doing the co-product twice and then doing the product twice after interchanging these two coordinates. Okay. All right, so that's the kind of structure that you have at the homology level, but we'd like to see this at the chain level. Okay, that's where Hopf infinity algebra will appear. Oh, I forgot to say modules. So now let's say you have such a Hopf algebra H. A module would be, I mean, for us, there are different ways to define a Hopf module, but for us, it will be something that comes equipped with a product and a co-product, and the product goes from H times M to M, while the co-product goes from M to M tensor M. So notice that there is no H in the co-product. Okay, and the analogous relation, compatibility relation between these two structures will look like this. Okay, so if you do the product and then the co-product, it's the same as doing co-product twice and then product. And here, notice that you need the co-product of the group. Okay, so this one is delta. That's the in the infinity algebra. In the Hopf algebra. So okay, and now I'll tell you that this is supposed to be related to instanton theory. So I think that this should be used to define a version of what we could call cornered instanton theory. Okay. And this is something that should be analogous to what was defined in hierarchy theory by Douglas, Lipschitz, and Manurescu. And here is how it is going to work. So I'm going to draw a diagram with higher categories. So here there is a a cobordism 2 category, cob 1 plus 1 plus 1 plus 1. No, it doesn't work. Yeah. So here, basically, you will have objects will be one manifolds, closed one manifold, and then morphisms will be two manifolds with boundary, and then three manifolds with corners will be these two morphisms, etc. And ultimately, we want to add dimension 4 here. But so in previous work, I constructed a functor from this category to a 2 category that I call Ham. Ultimately, it should be a 3 category, but it is of geometric nature in the sense that I mean, I'll tell you later how roughly it is defined, but it lies in the world of symplectic geometry, and if you know this category, it's very analogous to a category that was introduced by Moore and Takikawa. Okay, at least at the one morphism level, it looks like the Moore-Takikawa category. Okay, so I have constructed such a functor in previous work, and now we would like to land in something more algebraic. Okay, and we don't quite know what this 2 category or 3 category is, but we know that we would, if we're able to construct it properly, we'll call it Hopf infinity, and I'll tell you why. Okay, and then current instanton theory should be obtained by composing these two functors. Okay, so I'd like to give you an idea of what we have in mind and how we could construct this functor here that sends symplectic geometry to algebra. And I find it convenient to describe a toy model for this, because this is where Morph's theory happens. So I'm first going to describe for you these toy models. So there are easier categories here. So inside Ham, there is a simpler category that contains a category of Lie groups that I call Lie sub R, and it embeds on Ham by taking cotangent bundles. I'll describe for you later. And then, so this is supposed to be a chain level category, but you can take homology and you like in something simpler. Okay. And actually, I should say that I'm lying a little bit because these two arrows that are dotted, they are not quite functor in the sense that composition doesn't work well. So to actually get something well defined, you need to work at this level, at the homology level. Okay, but at least I want to give you an idea of what's going on by you looking at this toy model. I think it's instructive. Okay, so let me do that. So first, here I want to describe this red part of the former diagram. Okay, so this side is in the toy model that called Lie sub R, and there's no symplectic geometry here. And then the right side is in this category Ham, and then this is a functor considered. So here you have objects. You have one morphism, then you have two morphisms. So objects are just Lie groups. And then one morphisms are just smooth manifold with an action of G times H. Okay, so these are X and Y. And then if you have two such one morphisms, you have a notion of two morphisms, and you can take correspondences, just subset of the product that are invariant for the actions. Okay. Or if you prefer, you could just take maps from X to Y, smooth maps that are equivariant. Okay, so that lies in the differentiable category. And then to go to symplectic geometry, you can basically do the following. So you would send a group to itself. These form the object of the Ham category 2. And then one morphism, you would send it to cotangent bundle. Now that's a symplectic manifold that's endowed with a Hamiltonian action of these groups. Okay, so the one morphisms in this category are Hamiltonian action and Hamiltonian manifolds, and then two morphisms that will be sent to their conormal bundles, and these are Lagrangian correspondences. We'll see. So two morphisms here are Lagrangians, basically. Okay. And here is the way morphisms compose in these categories. So for example, if you have consecutive one morphisms in Lie sub R, you would just take the product and mod out by the middle group H. While on the other side, you would do the same, but you would take the symplectic quotient instead to get something symplectic. Okay, that's how it works. Okay, so that's the first part of the toy model. Now I'm going to describe for you what this arrow should be. And so this is supposed to be a simplification of what we really want, actually. Okay, what we really want is this, and I'm going to describe it later. But here, at this level, it's very simple. I mean, it looks very simple, at least what we want. We would like to send everything to the homology groups, okay? So in the sense that a group, for example, you would send it to its homology, and that's a Hopf algebra, okay? Then a one morphism, that's smooth manifold, you would again send it to the homology, and it will come with a Hopf by module action. And then a correspondence will correspond to a morphism of Hopf by modules. Okay, that's in principle what we'd like to have, except that there are problems in composition that should only work at the chain level. Okay, so that's kind of what we like to do. But now, so because of this problem, we should have a functor from here to here, and that will correspond to doing the Morse theory analog of what I just told you. And then there's the actual functor from Ham to Hopf infinity. And no, this is how it should work. Okay, so in this category Ham, you have the diagrams that can look like this. You have Lie groups, Hamiltonian manifold, and Lagrangian correspondence. And here, this is how they should be associated. So to a group, instead of taking homology, now you want to work at the chain level. So you would take the Morse chain complex of G and H. And now this should be what we call Hopf infinity algebras. And then to the manifolds M and N, the symplectic manifolds, you would associate to them the Fukaya category. So there are I infinity categories or I infinity co-categories for us, but they also come with this action. So in the end, there should be something like what we would call a Hopf infinity by module. And then to a Lagrangian correspondence like that, there should be an I infinity functor. I mean, so ignoring all the actions, these have been defined by Mao, Verheim, and Woodward. These are I infinity functors, but there should be more than that. In our case, it should be morphisms of Hopf infinity by modules. Okay, so this is kind of what we'd like to have, and just say that we're very early on this project, and what I just described you is far from being complete. Okay, but that's at least that's what we think it should. How we think it should work. Okay, any questions so far? No. So let me continue and let me give you a very, very vague idea of what we could mean by Hopf infinity algebras. So this notion already appeared in algebra, and it looks like it was, I mean, at least a definition was given by Sanneblitz and Humboldt in some situation, but it doesn't. I'm not sure what exactly the status is right now, but I'm not sure that the definition we really need actually appears. So there's still work, and we don't understand exactly what it should be, but roughly it should be something like an infinity bialgebra plus something that incorporates all the other operations in Hopf algebras that are units, co-units, and antipodes. Okay, but at least the notion of infinity bialgebra is well defined, and it was defined by Sanneblitz and Humboldt. And let me just say that it's complicated. But I haven't seen the the definition written explicitly, but I think it's possible to write. But roughly what this is a vector space with a family of maps indexed by two integers k and l. Okay, and these maps go from h power k to h power l, and then they satisfy some relations. For each k and l, there will be a relation, and these relations are determined by the combinatorics of some polytope. Okay, in analogy of the infinity relation are determined by the associahedron. These relations are determined by some polytope that they call the biassociahedron. Okay, so for any k and l, you have a polytope, and imagine that the relation look like that. So you, for each k and l, you have k input and l output, and you will sum over some complicated things here. I'm not sure exactly how it works and what counts and what doesn't count, but I mean, the polytopes should tell you this. And the observation is that such an infinity bialgebra contains both an algebra and a coalgebra. Okay, so if you specialize on L equals 1, you get an infinity algebra. And if you do P equals 1, you get an infinity coalgebra. Okay, and that's the structure we expect to have on the Morph homology of the Lie group. Okay, and now I'm just going to tell you how this would work. So basically, you will count graphs like the one we counted before. So in red here, you would have Morse flow lines, and you would either use the product or the coproducts. Okay, so for example, here you could look at a picture like that to see how the product and the coproduct interact. So basically, what is it? For example, yeah, if you compose the product and the coproduct this way or this way, you'd like to see a relation like that, but at a homology level. Okay, so you would look at to prove this relation, you would look at a one-dimensional moduli space that is parameterized by this biassociahedron. So again, so that's the simplest part of this biassociahedron that's not in the family of the associahedrons where either k or l equals 1. So on one side, you will have this relation. And then the thing is, what happens when L equals 0? And here something interesting happens, because this kind of moduli space, when you continue them, you would observe a picture like that. Okay, so that's one half of the biassociahedron. And then on the other half, you would count more complicated things. There are not graphs anymore. There are not trees anymore, but there are graphs, and they look like that. Okay, so here you have 4 segments, and you want them to all have the same length. And again, when L prime goes to infinity, they will break into something else that will give you the Hopf relation between the product and the coproduct. Okay, so but we still need to make sense precisely of what this infinite of this biassociahedron are in the model that we have. So let me. Yeah, so let me say that these biassociahedron have been designed by Sanneblies and Humble, but in an algebraic way involving matrices, and we'd like another more geometric realization that's more compatible to this Morse theory. But we expect that we'll get the right structure. Okay, so that will be the picture in Morse theory, but let me finish with the analogous picture that we will have in Floer homology. So basically, we will replace all these flow lines by strips, and then we'll get something like this. Okay, so that's one realization, and we'll get something that will look like this, where, I mean, well, blue will happen in the symplectic manifold, and red will happen in cotangent bundle of the group. Okay, so that's kind of the moduli space that should govern the structure of these Fukaya categories, and that's where I wanted to stop. So thank you.
Well, we should thank Guillem.
Thanks.
Of course, I'll leave it open if there are questions.
I have a question.
Yeah.
So I know Nathaniel Botman has been like doing work on like defining A∞ 2 categories to like have
Wait,
like.
Sorry, Ian, I had problems with my sound. I muted it. Can you repeat because I didn't hear the beginning?
Oh, sure. So Nathaniel Botman has been like doing work on defining A∞ 2 categories. I guess to like have a a category of all Fukai categories in some sense. Like, does this play a role in this at all, or is this or is that kind of like a higher?
Yeah. So definitely. So the thing is, this is how it works. So what you're referring to is the work of Botman. So let me just write Botman. Well, there is this Vanishing category of symplectic manifold. So there is simp. That's a symplectic category, and it should be something like an A∞ 2 category. Something like that. But in some sense, you can view this as a subcategory in the sense of Ham. Ham, not Hom. In the sense that, well, so this should roughly correspond to the endomorphism category of the trivial group. So this is a trivial group. Okay. So this would be an endomorphism 2 category inside a 3 category, and this guy should be an infinity, I mean, something that we call an infinity 3 category, maybe. Yeah. So, I mean, in particular, we'd like to extend this picture of Botman to 1 dimension below. Okay. But, I mean, well, as you already know, what Nate is doing is already quite difficult. We're not there yet.
Okay.
Does that answer your question?
Thank you. Yeah, actually did. I also have another question.
Sure.
If you could like break down like what the cornered TQFT should be in the instanton case, like with analogy with like, I don't know, like Douglas, Lipschitz, Manilescu's thing, like what's associated to a circle, to a surface, etc.
Oh yeah. So there is. Let's go over the. Oops. So here a circle first get mapped to SU3, SU2, and then SU2 will get mapped to the Morse homology. SU2 seen as a Hopf infinity algebra. And we don't know exactly what it should be, but as a vector space, maybe it would just be of rank 2. Yeah. And now the comparison with Higar-Floer homologies is very unclear, because in their picture they have something called Neal-Coxeter 2 algebras. So these are also algebras with 2 kind of products that are compatible in some sense, and at least I don't understand the relation.
Do you know if like their 2 algebra has like a Fukai categorical interpretation, like Aru's interpretation of the boarded Floer homology in terms of Fukai category of sim G? Like
No.
what? Yeah.
Yeah, no, actually I asked Cyprian, and yeah, it seems like they did it mostly algebraically, but it's unclear. At least I don't know.
Okay, thanks.
Yep. Other questions?
Okay, thanks for the talk.
Oh,
So I think so. You want to apply this story to the extended modular space, right?
Yeah.
So extended modular space doesn't quite fit into the symplectic assumptions that you said, right? So it's not a compact manifold unless anything.
Yeah, right.
It's not going to be monotone.
Yeah. So we haven't. So the thing is, where is it? Before. Yeah, here. So, I mean, this is still really work in progress, but so we're very far from trying to do the more general thing. So here is a simple set of assumptions that should work. So the thing, yeah, so for this extended moduli space, you have to do all these things that Manorescu and Woodward did, symplectic cutting, and you have a divisor. And I mean, it seems to me that there's no reason that this should not work. So it really looks to me that you could be able to do the same as what they did to the symplectic cutting, and it should work the same, I think. Unless you disagree. You don't seem convinced.
Well, we can talk more about it later.
Yep.
I mean, there are some technical elements, but yeah,
Yep.
we can talk about it.
Cool. Please.
Can you hear me now?
I can hear someone.
It's Piotr here. Hey.
Hi.
I wanted to ask, so the toy model for that is the picture of a compact Lie group acting on a compact manifold, and then you have, as you said before, first you get an A infinity module structure on the Morse complex, and as I understood, you want to even boost it up to get the Hopf infinity like object. So my question is, in this toy model, do you know how much of the topology of this space with Lie group action does this A infinity module capture, or do you know something about or do you expect something about the topology in the finite dimensional case?
Sorry, again, can you repeat what was the question? What?
Yeah, it's somehow what aspects of topology of this manifold with a group action does this A infinity module capture? To what extent do you know?
Oh yeah, I have no idea.
What extent does it determine the homotopy type and so forth? And do you expect the Hopf infinity thing to be much stronger?
I don't know. So the thing is, yeah, I mean, in particular, it contains the Morse complex. So and also the infinity structure given by these coproducts. So I suppose that it contains Steenrod square and stuff like that given by homotopy. But yeah, there is these other families involving the group multiplication, etc. Now I have no idea what it contains. Yeah, but probably contains a lot.